When presented with an NMR spectrum, you should be focusing on the four following aspects. First and most important are the number of peaks that are present in the spectrum. This will tell you the number of different hydrogens which are present by looking at the number of different peaks in the proton NMR, or the number of different carbons that are present in the molecule by looking at the number of different carbon peaks in the carbon NMR. Second is the chemical shift, or ppm value. That is where the peak resides specifically within the spectrum. This will give you information about whether maybe an aromatic ring is present, or the proximity of different hydrogens and carbons to electronegative atoms. In proton NMR, the range you're looking at for peaks would be anywhere from 0 to 14 parts per million. In carbon NMR, it's a much bigger window. You're looking at anywhere from 0 to slightly greater than 200 parts per million. Third thing that you look at would be the multiplicity of those peaks in the spectrum, that is the splitting pattern. For proton NMR, that tells you the number of different hydrogens which are present on carbons adjacent to the hydrogen giving rise to the peak that you're looking at. And in carbon NMR, this information is not always provided. And if it is, it's actually very helpful, because it will tell you the number of hydrogens which are directly attached to the carbon giving rise to the peak that you're looking at. Lastly is integration, and this is only for proton NMR. You do not see integration in carbon NMR, and this gives you information regarding the relative number of hydrogens which give rise to each peak in the proton NMR spectrum. Let's first begin with a discussion of how you establish the number of peaks present in carbon and proton NMR. The number of proton and carbon signals that are present in proton and carbon spectra indicate the number of different types of protons and carbons in the molecule. Non-equivalent protons and carbons give different NMR signals. Equivalent protons and carbons give the same NMR signal. Consequently, you should be able to predict the number of peaks that would be present in the spectrum of a molecule you're examining by identifying the number of non-equivalent hydrogens and carbons that are present in the molecule. There's different ways of doing that, but a simple way would be to play the substitution game. Examples are shown on this slide. What you do is you draw all possible monohalogenated isomers of the compound that you're investigating, and the number of isomers equals the number of different NMR peaks that you would expect. For example, if you take a look at butane, I label each carbon 1, 2, 3, and 4. If I substitute a hydrogen on carbon number 1 for chlorine, say, I end up with 1-chlorobutane. If I substitute a hydrogen on carbon number 2, I get 2-chlorobutane. So far I have 2 monohalogenated isomers. If I substitute a hydrogen on carbon labeled number 3, I get 2-chlorobutane again. And if I substitute a hydrogen on carbon labeled number 4 with chlorine, I end up with 1-chlorobutane again. So therefore, for butane, you would expect 2 proton peaks and 2 carbon peaks, because there are 2 types of hydrogen and there are 2 types of carbon, as demonstrated by this test. All right, 2,2-dimethylpropane. How many peaks would you expect in the carbon and proton NMR? If I substitute a hydrogen on carbon number 1 for a bromine, I end up with 1-bromo 2,2-dimethyl and if I substitute a hydrogen on carbon labeled number 3 for bromine, I end up once again with 1-bromo 2,2-dimethylpropane. If I continue substituting on carbons labeled number 4 and 5, you see that I'm continually drawing the same isomer, but just in different conformations. So all of those hydrogens and carbons would be equivalent. I would therefore expect one peak in the proton NMR. Now for carbon NMR, don't forget that you also have this quaternary carbon labeled number 2. And so you would expect 2 peaks in the carbon NMR, one for the methyl and one for the quaternary carbon. Let's get some practice. How many proton and carbon NMR peaks would each of the following molecules have? Again, as you go through this, stop the video and see if you can predict the number of peaks in advance of having them shown on the screen. All right, for this molecule, it's very symmetrical, and it's not too much different from this example that we saw on the previous slide. You can clearly see that we have 2 methyls. The 2 methyls are equivalent to each other. We also have these methylene carbons, which are also equivalent. And this is because, again, there's symmetry right between these 2 center carbons here, which would also make these carbons and hydrogens equivalent. So you would expect 3 proton peaks and 3 carbon peaks for the first example. For the second one, we have 3 methyls in the molecule, but it's only these 2 methyls here which are equivalent. This methyl is not equivalent. As we move through the rest of the chain, you can clearly see that we have unique sets of carbons and hydrogens. So in this case here, we have these equivalent methyls. Those are the only equivalent carbons and hydrogens in the molecule. So we have 5 different peaks in the proton NMR, 5 different peaks in the carbon NMR. Move on to the next one. This one we have 1, 2, 3 different methyls in the molecule. You can see that there's symmetry, a plane of symmetry that's bisecting these hydrogens and carbons, making these 2 methyls equivalent, but this methyl is not equivalent to those. So in this case here we have 4 peaks in the proton NMR expected and 4 peaks in the carbon NMR. This example is much more symmetrical, so you would expect to have fewer peaks in the proton and carbon NMR. So that's a general trend. The more symmetrical a molecule is, the fewer peaks you would expect to see in its NMR spectra. In this case here, if you played the substitution game, you'd find that all 4 methyls are equivalent to each other. There's a plane of symmetry going down the middle of that molecule, which would also make those carbons and hydrogens labeled number 2 equivalent. So you would expect 2 peaks in the proton NMR and 2 peaks in the carbon NMR. For the last example, we have 4 methyls. If you look a little more closely at this, you can see that these 3 methyls are going to be equivalent to each other. This is a tertiary butyl group, so all of the methyls in a tertiary butyl group are going to be equivalent, which would make 3 peaks in the proton NMR. Again, don't forget, in carbon NMR, you also have you might have carbons present which have no hydrogens attached to them. So in this case here, we would have 4 peaks present in the carbon NMR. When analyzing molecules for their NMR spectra, we have to consider their 3-dimensional shape, their stereochemistry, and this is especially important when you're considering the structures of cycloalkanes and alkenes. We have to remember that a ring has 2 faces and that a double bond has 2 sides. For example, take a look at cyclopropane. Very symmetrical molecule. If you play the substitution game on this, you'll see that all the hydrogens are equivalent and all of the carbons are equivalent, so you would expect 1 proton signal and 1 carbon signal. If I substitute one of those hydrogens for another substituent, for example a chlorine or something else, I've destroyed some of that symmetry. So now we have hydrogens which reside on the same face as the chlorine, and we also have hydrogens which reside on the opposite face of the chlorine. There's still some symmetry here. These 2 hydrogens labeled HB are equivalent to each other, and these 2 labeled HC are equivalent to each other, but they're not. But HC and HB are 2 different sets of hydrogens, and we also have HA, which is the hydrogen on the carbon-bearing chlorine. So you would expect in the carbon NMR to have 2 signals, and in the proton NMR, 3 signals. Take a look at this alkene over here. It's very symmetrical. We have hydrogens on this carbon. This one is on the same side of the double bond as chlorine, and the same thing for this one over here. So they're equivalent to each other. We have 2 different types of carbon in the molecule, clearly, so we would expect to see 2 carbon signals, but only 1 proton signal. If I have a monosubstituted double bond, as shown in this example, I've destroyed a lot of the symmetry. We have this hydrogen on the same side of the double bond as the chlorine, which would be not equivalent to either of these hydrogens. And these 2 particular hydrogens are also not equivalent to each other, even though they're on the side of the double bond opposite the chlorine. HA is on the carbon attached to chlorine, and HC is not on the carbon attached to chlorine. So we would expect to have 3 proton signals for that molecule, and of course 2 carbon signals. How many proton and carbon signals would you expect each of the 3 molecules to have? And don't forget that the hydrogen attached to oxygen would also show up in the proton NMR. Let's start with the one on top. If the methyls are equivalent, we have 1, 2, 3, 4, 5 proton peaks, and you would expect 1, 2, 3, 4 carbon peaks. Move on to the next one. Again, if the methyls are equivalent, you would expect, and they are, and you would expect to have 1, 2, 3, 4 proton peaks and 1, 2, 3, 4 carbon peaks. See if you can predict the number of proton and carbon peaks for this example. If you predicted 5 proton peaks and 4 carbon peaks, you'd be mistaken. Let's go back and take a look at the examples above to see how we established that we actually had the number of proton and carbon peaks that we predicted. These 2 molecules have a mirror plane, a plane of symmetry, which is going along this axis that I'm showing here with the laser pointer, which means that in the upper case, these 2 hydrogens are equivalent to each other, and the 2 methyls are equivalent to each other. So these 2 methyls are definitely equivalent to each other because of this symmetry. And the same thing for the second example. But the third example has something else. It has an asymmetric center, right? And asymmetric centers cause asymmetry in a molecule. And once you have an asymmetric center, you should expect to have more peaks present than you might have predicted. For example, if we look down this axis now in this molecule with an asymmetric center, you can see that the 2 methyl groups are not equivalent anymore. There's no mirror symmetry in which they reflect each other. If I rotate around that axis between the CC bonds right here, the 2 methyls are still non-equivalent. And I could rotate this all day long and they would never be equivalent. So this asymmetric center is making these 2 methyls non-equivalent, giving you more peaks than you might have predicted. So the lesson here is watch out for asymmetric centers, and if you play the substitution game, you will actually see that you have 6 proton peaks and 5 carbon peaks for this particular example. So why is it that the methyls on this molecule are equivalent, but the methyls on this molecule are non-equivalent? If we play the substitution game and we substitute the hydrogens circled in red one at a time with a group Z, you can see that we end up with enantiomers. If I substitute the hydrogens on the methyls circled in blue with a group Z, I end up again with enantiomers. Right, we know that enantiomers will have identical NMR spectra, so therefore the hydrogens attached to these carbons are said to be enantiotopic, and they will give a single NMR signal. For the example below, because of this asymmetric center, if I start to do substitutions like I did above on these methyls, I end up with molecules which are not enantiomers, these are diastereomers. These hydrogens are said to be diastereotopic because substitution of each hydrogen with a group Z would lead to diastereomers, and they would give 2 NMR signals. So this is something that you can look for when you are analyzing NMR spectra. Once again, if you have an asymmetric center, play the substitution game, look for enantiotopic and diastereotopic hydrogens and carbons.